So welcome back. We did the first session on short training course on machine learning for spatiotemporal data. The first session was basically about spatiotemporal data, what's specific about it. And I also show you some examples, how you visualize space-time data, what are the strategies to visualize. And then we also spoke about complexity of time dimension, how you do time series analysis. This is the second block. Here we will also do a bit of introduction to modeling with spatiotemporal data. And specifically, I will focus on doing spatial interpolation. I call it spatial interpolation, but in general also later on we will be doing some regression or classification. So that's the focus of the second block, and then the third block will be after lunch. We'll be doing basically ensemble machine learning. So we go another layer of complexity. And for those of you who are new ensemble machine learning, I will explain you that. I will show you how it's done efficiently in a framework and how you can basically combine multiple learners and also look at the effects of that on the accuracy and go step by step. So that's the plan for the second block. So I will, in this session, I will also show you how we can model seasonality effects. And we have a little formula that allows you to model seasonality at every point on the planet surface. Then I'm going to talk a bit about machine learning, what are the standard steps. Then I have a really nice example with the synthetic data about the extrapolation and overfitting of machine learning. Many people start using machine learning without being aware of all the, let's say, dangers of using machine learning. And then they sometimes, because it's very complex and it looks like a black box, I notice some people make a predictions or some results and even send a paper to publish. And then they discover that there was overfitting or there were some artifacts. And that can be quite a problem, especially when the paper is already accepted for publication. So, so that's why we're going to talk about it, how to prevent that. And then I will show you the spatial interpolation. I will show you the thing that I used to do in geostatistics using Kriging, fitting variograms, etc. And I will show you how does it look, how you do that with machine learning. So something I specialize with, and the last paper we published went really viral. So it receives now over 100 citations a year. So people got really interested in that. And we kind of make a bit Kriging redundant because we have a more flexible method to do spatial interpolation. So that's the program for the second block. So this is the data set I was showing you. This is this Cook farm. It's a 4-dimensional data set. And as you see, when you look at many space-time data, especially ecological data, you will see the seasonality effect. And so that's very interesting. So it's very regular, let's say, but it differs a bit, seasonality. Also, when you look at the seasonality, if you have a winter in Europe, in Brazil, it's summer, southern Argentina, let's say, it can be summer. So it's completely opposite. So the climate is also, even seasonality of climate is very complex. You know, you have tropics, you have moderate zones, you have a southern, northern hemisphere. So also even this seasonality is complex. And so I'm super happy we published this paper in, let me see, 2014. Milan actually is a first author. It was part of his PhD. So he tried to tackle that problem of seasonality of daily temperatures. At that stage, we were just focusing on daily temperatures. And he came to a formula. I don't know if you ever saw this, but imagine this temperature, daily temperature, anywhere on the planet. Actually, it's you can kind of model it based on the angles. So it's a kind of sphere geometry. And this is the formula. So the two formulas. And if you put the coefficients of these formulas, then below here you can calculate minimum daily temperature and maximum daily temperature. So you, as an input, you only need the latitude. You need the latitude and you need the day of the year. if you know just the latitude and day of the year, you can model global temperature. And that way you can also model the difference between southern, northern hemisphere, tropics, etc. So I don't know if you ever saw that formula. I'm still not sure if he derived the formula first time. I think he saw pieces of the formula and then he combined it together, and then he made it as a single thing. And you can put it in R, and this is how it looks like in R. So this is a mathematical notation, and this one is in R. And you can also estimate your own A and B parameters. So you can also estimate them. So I think that's kind of some type of a maximum minimum temperature at the 0 latitude or something. But you could put that estimate your own parameters. And then if I go to the RStudio, so that's this modeling seasonal components. You can see that we put that formula here. Here's the formula, and as you see, I can go and let me see. I can go and run that formula to some arbitrary day. So let's say if it's a 52 degree, which is we are now 52 degree, then I get for day 120, I get 8.7 degrees, the minimum daily temperature. But I could also put it somewhere in the 22 degrees. I don't know, somewhere in Morocco or something. Let's see. Yeah, I deleted something wrongly. Let's see. Looks like this visual editor, it's not working. So let's say 22, and if I compute it, I get 23. You see? So it will change, and I can also play with the day of the year. So I can just keep on changing these numbers, and you can play a bit with it. And what happens? You get constantly you have a different number. So that's basically when you put it in this formula like this. That I take 5 years. Right? I take 5 years and I say, I want to look at the 52 degree norths and I want to look at all the dates, then I will get this this plot. And so that's the seasonality. And so this formula, by the way, I can plug in and compute for pixel. So I can also make images, because you see it changes with the latitude and day of the year. And so I could do it for every pixel. And then I could basically map the temperature, geometric temperature for the Netherlands for every moment. So a very useful formula. And we discovered that you can actually use it universally. Anywhere you have a day or monthly values. So let's say for the land cover for these predictions here, we also use this geometric temperature as the covariate. Yeah, so we also use it to model the land cover and the forestry species, etc. So we can use it for forestry species. No, we didn't use it, but because it's annual. Annual doesn't make sense to use, but we use it for the land cover, because land cover we can model per season. We know the seasonal changes. So then you can use it as you can basically add it as a covariate, and it helps you. It helps machine learning because if you miss any other parameter that, especially for larger areas, that basically represent the latitude correctly. Because if you use directly latitude, it's not the same, right? Because latitude, it's like an X dimension. And then if you go, for example, from latitude 42 to 52, you move for 10 units, but actually that's not one-to-one to changes in the temperature. You know, if you move from the 42 degrees to 52 degrees, and from 52 to 62 degrees, then from the 52 to 62 degrees, the temperature drops much more rapidly. Okay, so you don't model the latitude then correctly. But if you apply this formula, these trigonometric formulas, then you can model really seasonality effects much more, I think, realistically. And that's why this formula is it's super important. And as you see, this is when Milan took the actual data on the meteorological station. This is super interesting So what you see is, let me increase this. So what you see here is the gray line is the actual measurements of daily temperature at the station. So you can see the temperatures daily, they can differ from day to day. I mean, you can have some rainy periods, cooler periods, warmer periods. So they differ, like within 1 week, you have a bit cooler, a bit warmer. And then this one is the MODIS, the broken one. The MODIS is a bit overestimating temperature, looks like. So it's a bit above for these 2 points at least. And then the geometric temperature is the very smooth line. Yeah, that's the geometric temperature. And you see the geometric temperature, the actual daily temperature reflects very well. And he was surprised that when he made this model for geometric temperature, he took the global data set and he said this geometric temperature explains already 80% in variation in values. So you can already, with the geometric temperature, you already, 80% of values you can predict. So that is a nice proof of concept of that formula. But of course, there's a remaining variation that you would like to improve. And then the final prediction is to do this linear model. And this linear model, so it uses the geometric temperature and MODIS, and it makes the prediction in between. You see, that's in between the MODIS and geometric. And that's kind of already ensembling. You basically have two predictions of the same thing, and you're doing ensembling, and then you see that you come closer and closer to daily temperatures. And that's what he did in this paper, basically. That's the work. And so we really like that, and it's a very good response. And we started later on, we started using that geometric formula. We can use it universally as a covariate for any modeling where you have seasons or days. Yes, so you can use it universally, basically anywhere, as long as, I mean, if the area is very small, then the effect of latitude will be very small. Then there's probably no need to use. But as soon as you move to an area, let's say size of Netherlands, then it makes every sense to plug in that as one of the components. And you just add it to machine learning. Okay, so I started with the geostatistics then about 7-8 years ago, maybe a bit less. I kind of started switching to using machine learning for predictive modeling. And this is the general framework that we still use basically for the machine learning for predictive mapping. It has we put about 8 steps, and you can read about this in this article. But let's say the first steps will be to define area of interest and variables and consider all the inputs that you will need. And then you, based on that, you make an implementation plan. And then the second step is to prepare the covariates. That can take a lot of time, and also to prepare all the training points. And so that can take a long time because you have to prepare Earth observation data, etc. Then you could, if you don't have the points, then you could do a new sampling. Then we use a Latin hypercube sampling. That's the usual we do because it's let's say, most suited sampling for a multivariate regression problems, classification problems. And then we do the field work, you collect data, and then you do overlay. In the case of SpaceTime, you do SpaceTime overlay. And sometimes you need to also make covariates which have this, let's say, some road network or accessibility for the Latin hypercube sampling. And then you create this regression classification matrix. And then from there on, it's just machine learning. So if you do everything properly, then you have the machine learning, and then you can generate also maps eventually. And then you look at the accuracy and you look at the patterns and you say, well, we have a problem. This still doesn't work still. Then you could go and collect maybe new points, extra points, and then you remodel everything. If you code everything, if you do reproducible research, every step is in code. Then eventually when you finish the coding, if you add more points, then it's just rerunning and repredicting. And that's a general framework we use for predictive mapping and modeling. So more or less all our examples, everything also you see in this training material, more or less all follows the same principle, except often we don't have an opportunity to go new sampling. So that's a pity. Sometimes the samples, they are defined how defined. So, and sometimes they are purposive sampling, and there's a bit of clustering, and there's a bias over representation of areas, and that's a problem. And there's some remediation techniques for that in machine learning, but you cannot do, sometimes you just cannot do magic. Sometimes we just doomed to have to extrapolate and predict outside of the, let's say, feature space that we have for training. So that's the general approach. And then this is also just in text inside the machine learning. So just if you zoom in on this part, so level 7. So if you zoom in on that part, so what you have here is the, you do the fine tuning. So you can do fine tuning, you can do feature selection. So you try to reduce model complexity. You can also do learner selection. So you can just test the learners that are more significant. So you can do many steps. And then it's also very good to do kind of cross evaluation, cross validation. And then you estimate what is really your uncertainty and what is the most important variables, etc. And then you generate predictions, and then off you go. You make a web GIS, and you get this thing. And then people can, access it and use it. Notice that most of WebGIS we make, it has also a URL bookmarking system. At the moment is without authentication, so it's really purely open. But we might put some session ID, so at least we know if you have a bug. You said I had a session last week and I had these problems, so we will put some session ID. But if I just copy this URL. And I send it to some, if I open it in a new browser, if I send it to colleagues, when they click on it, they will get exactly the same view. And that way you can communicate about the same problems without even understanding GIS and SpaceTime and I don't know. So that makes it very accessible to also to non-experts. So that's something I think we find increasingly important. Okay. When I started using R, I noticed one of my favorite books at that time was the Covariate book, Covariate package book. I don't know if you ever use it, but it's very systematic, and I think it's the best way to understand, also as an introduction to machine learning. Although many of the techniques here, they come really from statistics, right? And this book, the beginning was about classification, regression trees, modeling different type of regressions, which are like can be even just standard GLMs and I don't know. So this book, I really enjoyed that book, and it was let's say a mind changer for me, and I started really thinking about this, how it's very important to do the cross-validation, repeated cross-validation, refitting. So many times try to do from different angles, and then learn from there. And that's how machine learning works. Machine learning is a hybrid between computer science and statistics. And so some techniques, machine learning, actually, they're really just statistical techniques. They're just combined into computer science techniques. And like three common computer science techniques in machine learning is, for example, sorting, then let's say finding a pattern, finding a combination that has a best matching and things. And then learning is, making decisions based on repeated cases, making some decision based on some, let's say, threshold values. These are like computer science things. But then RMSE, ordinary least squares, fitting technique, this is all from statistics, right? So then when you combine the two, you get machine learning. So please take a look at that Covariate book. I highly recommend it. So when you look at this framework, we do a lot in this framework. This is purely spatial framework as you see it. So how do you apply that framework to space-time? And there's an extra layer of complexity. How do you do Latin hypercube space-time? It is possible to extend Latin hyper to space-time. Also, how do you do machine learning on space-time data? So it looks like I showed you the space-time data is more complex than spatial data. But actually extension, you will see many extensions to SpaceTime. They're not so complicated. So as long as you pick up the key things that are kind of represent the difference. So one of the things I showed you is the seasonality. Yes, and I showed you that seasonality, you can represent it with the, for example, geometric formula, and you can plug it into a spatial data. So we can also estimate it for every grid cell. Yes, and then in that way we represent seasonality in our raster model, raster stacks. Okay, so and that's a very efficient way to then represent that in the spatial temporal data. Then the other thing is when you do, for example, overlay, spatial overlay, which is relatively simple, let's say. When you do space-time overlay, we made this extra functionality that allows us, it's called extract st. So I made a little function, which basically adds a bit of complexity, but allows us to do a space-time overlay. So I still use, basically I use a spatial overlay, but I made this little function that extract st. So here's the function. So I made this little function that I subset the points in space-time. So if I have a raster, imagine I have a raster, and this raster has a begin-end date. So it applies to some begin-end date. Let me put it here. So if I have a time series of rasters, yeah, if I want to do space-time machine learning, obviously if I have points, remember points are like in a space-time cube. So let's say if this is the space-time cube, so the points can be different places in the space-time cube. Yeah, so you have imagine it's like a multiple rasters, and then you have the points. And now I want to overlay. So I need to know for these rasters, I need to know to which time period they apply. So let's say MODIS images, temperature images, there's an 8-day. So they apply to the 8-day period, 8-day, yes? But my points, they're daily, okay? So my points are daily and these ones are 8-day. So I have to subset first all the points that fall into the time period. Then I get a subset of points. If I have 1 million points or 1,000 points, then I take the points that fall into the 8-day period. Okay, and now I have a x, y, t points from the original x, y, t that fall, so that's like a subset. So let's put it something like S. So this is a subset, and these points I can now overlay with this raster, and then it becomes just a spatial overlay. You understand? So actually it's not so complicated, space-time overlay. You just have to match. You have to match points first in the time, then you match them in the space. So first the time, and then you match in space. And then you do overlay. Yes, and then because it's the large data, what this function doesn't do any parallelization. This function is just simply extract first subset. Subset here is the select is the subset. So I said it has to be less than the upper date and more than the lower date. Then it subset the points, and then I do extract, which is very fast. Yes, Terra package extract. So just the points over the raster. And then because it's a very computational to do it sequentially, then I make a function that goes and does that. So let me see, where was I showing that here? Sorry. Then I make it in parallel with the parallel package. There's an MCL apply. I make it in parallel. So if I have a time series of 1,000 images, then I will just run it as fast as possible. And then my overlay will be as fast as possible. And you see, it takes literally to overlay 155 points going through 1 year data. So lots of space-time points. I can overlay within seconds. And that's what we do. That's the stuff I kind of created over the years, and now you can just go and use it. It will allow you that in R you can do as fast as possible I don't know if it can get faster. Trust me, I try many things. This is the fastest with using the default packages for spatial analysis. This is as fast as you can get. And you can do the space-time overlay. And as an input, you only have to say, what is for every TIFF, you have to say what is the begin time of a TIFF and the end time of a TIFF. Yes, the only thing you have to say is this. And then you put it here, you say, this is the list of images. And then for each image, you do overlay versus the meta values. And this is the begin time of a TIFF, end time of a TIFF. And then you do the overlay. But we're going to show you that. We're going to run that example in the last block, and then you can look at that. So this is the way. So another way to move from space to space-time. So we do a bit. So we add the seasonality, and then we do the space-time overlay. And then once you get the space-time regression matrix, actually then machine learning, it becomes it's the same, or more or less the same, except you have to be aware it's a space-time always, but more or less the same principles applies. So you solve a couple of methodological problems and you get to the machine learning regression classification matrix, and from there it becomes more or less the same. Carmelo, can you please close the door? Then the issue becomes that the data becomes very, it becomes very large. That is one of the issues, and that's what I told you. And you will see it in this when we do training. I mean, look, I have 155 stations, but it's a space-time problem. Suddenly I have almost 45,000 values. And you say, okay, 45,000, nothing. But imagine when we had 7 million space-time points, and we have 7 million rows with 300 covariates. And that's a problem. I cannot open that in laptop. I cannot do machine learning on my laptop. Then you slowly have to move from using just PCs, whatever, to using high-performance computing infrastructures. And we don't, of course, any of our project, we don't compute anything on computers. We use all the servers, right? But we will test, we will make the core development. We subset this space-time regression matrix. We subset it 2%. And we do core development. You can do it on laptop. That's fine. And once you're done with that, then you put the 100%, you put on some computing infrastructure. And computing infrastructure, everything we use also runs Ubuntu. Actually, you have a GUI. You log into this computing infrastructure. It also looks like a GUI, and except it's the servers that cost, I don't know, 50,000 US. So you have to be careful what you do. But this is the space-time, going from machine learning to space-time. So I got really interested, of course, in machine learning. One of the reasons, automation. Why automation? Well, you want to retire earlier and have more free time, obviously. That's why we like automation. So we have to do, well, you definitely with automation, you want to do less repetitive work yourself. Okay, everything basically in science and in life, anything you can automate, you should automate. It doesn't, I think repetitive processes, they are good sometimes for meditation, they're good for relaxation, I don't know, but they're not good for creative growth. So they are not good. So any work, anything we go, like if you imagine today people sit in the car and they drive to work and drive back, it's really bad. It's really bad for brain. I mean, unless if you meditate in the car. But let's say if there's nothing to meditate and there's no interesting radio station, it's a waste. So it's best that we use our brain only for the creative things. And so anything you can automate, you should automate. So I really like that about automation. Then machine learning, it's also, I think, sometimes we had in statistics and in the classical methods, they're very limited, so they're not so flexible. So sometimes I heard in sciences that even people look for data sets that match their methods, right? There are people who say, well, I have this method, I learn how to use it, but it has limits. So they will only look for the data sets that match their methods. And of course, that's a wrong way to go in science. In science, the right way to do, of course, is to look at the complexity of world and then see, okay, how do I represent that complexity? So like if you look at theory of chaos, if you look at, I don't know, chaotic behavior of, I don't know, stock exchange or climate, and I don't know. So you say, how do we model that? You know, that's a much better way. And if you look at the many things in the world, you need models which, for example, can represent non-linear relationship, different distributions, different type of covariates, many covariates, everything influence everything. And that's where these models come. The neural nets, random forests. These models have a capacity to have many variables overlap. The relationship can be complex. And actually, when you look at just the random forest, actually it's so generic, you can apply it to regression problems, classification problems, survival modeling, whatever. So it's also very generic in sense of how you can apply to data. And that's what I got really interesting. The problem with the machine learning is computational complexity. So the computational complexity I had when I did some linear statistics and geostatistics, as I said, it was an order of magnitude less, even sometimes 1,000 times more computing. But computers, if you look at them, you know, we are now somewhere at 2021. You know, when they started, I don't know, this was the first computer, IBM tabulator, I don't see the year, wait. So this is something 1930 or something, and then the first IBM computers, 1950, and you know, the operations they could do. So they were very basic. And now they say, oh yeah, you know, this Apollo, the space mission, you know, that had also computers that spend billions of dollars, and now you have the same computing capacity on one iPhone, you know, the same computing capacity from 1960s. So when you look at further down the road, 2045, we are now getting closer to the brain power computing. I don't know how they estimate this computing. I don't know what is here on the Y line. But apparently by 2000, let's say 30 or something, we will surpass the capacity of brain computing. In 2045, we will surpass because it follows this Moore's law, exponential growth. By 2045, we have computers that can think at all people ever born at once. So that's a bit scary. And there's even this, Ray Kurzweil wrote this. Have you ever seen this? It's like a 6 epoch. And so we are now somewhere in between epoch 4 and 5, where technology is basically combined with biological life. And then when it gets to the high level, so you will see the biological life will disappear slowly, and you will have just a technology. And then you will have this highest level of intelligence, and it will have a capacity to spread around universe and also terraform the universe, not by traveling, not people traveling in sci-fi movies, but just by electromagnetic light. It will transform the whole universe and turn it into a supercomputer. So that's the 6th epoch, and that's called universe wakes up. Anyway, read about it, but that's a real extrapolation of Moore's law, and many people don't buy it. Not every exponential growth is good. The CO2 emissions, very sad to see, you know, it's very exponential plot also. The CO2 emissions and population growth a bit slowing down, at least they think it's going to slow down. But CO2, it's been now from, I don't know, this Rio meeting and Kyoto Protocol, there's all these meetings and we still emit CO2 exponentially more. Now the exponential growth started slowing down, but we still emit every year more and more. So that's a sad thing to see. But me back in 1999, I was very excited about geostatistics. Okay, so when I started Kriging and I was learning, I followed 2 courses. And then I published some work on maybe combining Kriging and regression and applying it also to space-time problems. So I slowly published, and then we started doing bigger and bigger data sets. And then I switched 2013. I wanted to do geostatistics of Africa And then I saw, oh, I don't know, I'm going to do this, and points are clustered. So we just did the random forest, and I saw random forest, so I get a better accuracy. So it looks like it's more suited for this type of problems. Then I did some global data sets, and from about 2018, I stopped. I don't use so much geostatistics. I only use it for teaching. The problem is in science is that my most cited work is in geostatistics. So when people see me now, they say, oh, you're the regression Kriging guy. So that's what people tell me. Oh, you know, in science, when you reach a level, people publish, people cite you, then you become the term. You know, you're not your name or something. You know, you're this guy or that guy. You become a term. So I was the regression Kriging guy, and I said, look, I stopped using in 2018. So officially, I'm not. You know, it's like with Edzer and our people, they made this SP package and but they dropped it a bit. So now, oh, you're the SP guy. No, I'm the SF guy. Right, and also Robert Hymas, he made the raster package. So yeah, you're the raster package guy. No, I'm the Terra package guy. So these things also change. But unfortunately, there's a bit of echo delay, and so I'm definitely not using random regression Kriging and stuff. So I'm much more interested in machine learning. This is just to show you, like at that stage, you know, I looked at the ordinary Kriging. And I made this paper called Mapping Efficiency Information Content. So what we saw that if you plug in this regression part and you combine it with Kriging, you get the map on the right, and then the uncertainty drops. Here we kind of visualize the uncertainty very simple. We mask out the pixels that have the error larger than the variance. So we kind of mask out this pixel because it means like you don't create any significant prediction. And when you switch from this model to this, you can see that you can map more pixels. So very simple. And you can see the patterns, you know, they're a bit changing. It becomes like more and more detailed. So that was this paper. So that was, that time I was really excited about that. And then we started looking at this using a random forest to do interpolation. So basically, not as a combination of geostatistics, but really just as a replacement. So I just want to show it. So this is like this Kriging technique. Do you use Kriging? Have you used Kriging? Yes? 1? 2? No? No? So in Kriging, so you have the points and you fit a variogram. Variogram is a model of the spatial dependence. You need to decide about transformation. So you have to understand geostatistics. You cannot just like, I'm just going to do geostatistics. So you have to know what you're doing, but many choices are on you. So you have to pick up the transformation of data. You have to pick how you're going to fit the variogram. You want to do anisotropy, yes, no, So you have to pick all that up, and then you fit a model, and then you get the predictions. And let me show you, and then the regression Kriging is to add to that also regression model. But let me now show you how it looks like. So when you do model-based statistics, you know, you say it's a GLM, you have the transformation, you have you have to specify the covariates you're going to use, and you have to specify this link function. So you have to put all this stuff. This is this model-based statistics or geostatistics. And then machine learning, very different. You just say, I want quantile regression random forest, and off you go. Okay, so very, very different. And there's a famous article by Leo Breiman called Two Cultures, and you should read that. It's a really classic if you want to get into machine learning without reading that article, and also the other articles that follow, discussion articles. You will never get to machine learning. So please read that Leo Breiman, Two Cultures, and basically, so what he says that these two cultures, just to summarize it, in both cultures, they have different obsessions, let's say, and they see the aesthetics of things differently. So when you do model-based statistics, let's say, so like just when you think about Gaussian distribution, you represent it with how many coefficients? You have the mathematical formula for Gaussian distribution, and then how many coefficients you have? Do you know? So it has two coefficients, the mean and the standard deviation. So you have mathematical formula and you have two coefficients. And this is beautiful. You have something which is used in statistics all across, right? And universally, many fields. And it's you can represent it with two coefficients. And the beauty of that is the simplicity. two coefficients and you model different distributions, then you can have maybe a skew distribution, I don't know, you can add the coefficient, but otherwise the most simple case, you have two coefficients and you model the distribution of errors, the distribution of anything you measure. So it's really beautiful when you think about this. So the beauty in the model-based statistics in the figure out what is the simplest possible way to present something universally. And that's in the case of Gaussian distribution, that formula that Friedrich Gauss made, and he says it's two coefficients. I mean, maybe it could be done in one coefficient, I don't know, but two coefficient already is very simple. When you do machine learning, it's a different direction. You don't mind that this random forest, it can have 1,000 parameters. You don't mind. It can have many parameters, because the beauty is how good you learn, how good you match the data. That's why it's called also data science. It's not the essence is to understand the models. You have very generic algorithms that come from mixture of computer science statistics. You have very generic algorithms, and then it's just how efficient are you in finding the structures in data. Yes, and that's the second culture. You don't worry about the beauty of the models. You don't worry if there's if it's Friedrich Gauss or if it's 1,000, if it's two parameters, it's no problem. Yeah, but you do way more computing. And so these are these two cultures. And I kind of switch to that. Yes, question? Yes. Similar outcomes. I don't think you can easily say this technique is data science and this technique is model-based statistics. Sometimes there's a transition, right? So there's some things that have elements of learning and repetition and sorting, and then some has elements of just this is the model, and we just define the minimum complexity model, and that's fine. So I don't know if there's a straight line that I could say. I don't think so. So it's a bit of fuzzy term, But INLA, yeah, super interesting. And INLA, I think you can combine it in ensemble system. You can put it in ensemble system, and then becomes one of the learners. And then you apply this data science, machine learning on top of it, and that's fine. So that's how I would do it, right? So if it does work, but I think this Bayesian methods, as far as I understand, you need to know for every observation, you need to also know some uncertainty or some prior, I don't know. And that makes it complex because you don't have it for many data. So it's a specific method that you can assume that it's all the same or something, I don't know. But the real effect, if I understand the Bayesian correctly, the real effect is if you know these priors, if you have them like first estimate, or if you have diverse uncertainty data, then you have the real effect. Because that's the thing you don't get so much good in machine learning, right? That's how I see it. But I haven't used INLA, so I cannot, give you a more detailed answer. I haven't personally used INLA. This is the GOR package, geostatistics. So the same thing as I was showing here, more or less, but this was just a regression. Now in geostatistics, you specify the lambda, which is, if it's a lambda 0, it means a log normal variable. And then you have to say this range of you want to use to fit the variogram, and you have to say which variogram model you use. So you have to specify these things. And then you fit the variogram, and then you do the Kriging. And then you have all these steps. It goes fit the model, do the box transformation, then run the Kriging, etc. And then variogram, sometimes you have to do anisotropy, so you consider also extra parameters of variogram anisotropy. And you can see that it is sometimes in different directions. The variograms can be different, like the red and the blue, they're quite different. So sometimes you have to do all these things. And so what I started looking at, okay, let me now look, what if I just do like this? It's I just take buffer distances to points. I take the points and I take buffer distance to all the points. So there's this formula. And then I run random forest on this. So no, I don't have to know any geostatistics. I don't have to pass any parameters. There's nothing. It's just fully, totally automated. Nothing. I don't have to, no model, no modeling assumptions, no distribution, nothing. Okay? I just say, here are the points, buffer distances. And this is what I got in the beginning. The left one is the state of the art, cutting edge, geostatistics. The one on the right is just random forest on distances. And I showed this to a few geostatisticians, and they, wow, this looks quite similar, right? And first, what is similar is smoothness. So machine learning finds the smoothness in the values, right? The values, they could be changing, like, or the shorter distances or longer distances. So it finds, like, it's almost like recognize the variography, you know, and it matches it. And then in between the values, it's kind of like the values, like interpolating. And I repeated that for many data sets. And so again, universal Kriging, random forest. Here you have even an isotropy. It's a one famous data set. It's a very anisotropic, so you have to model anisotropy in variogram. And then the machine learning find also this anisotropy. You see, it will find that the values change more in this direction than in this direction. Okay. So and you can estimate also the prediction error, which can be quite different from Kriging. So you get more details. So I got very interested in that. So I said, wow, this with machine learning, with the Kriging, you have these stationarity requirements. The distribution should be normal. Then you have to fit a variogram. Then you might have some hotspots, and they can be a problem, and you have to do something in geostatistics. And with machine learning, none of this. Actually, you don't even have to fit any variogram, nothing. And actually, you can also extend it. You can add more complex distances. You can add also distances in the watershed. You can add distances to some sources of pollution or something. So you can put everything together, which you cannot do in the geostatistics. So you can just throw it on a pile. It's unbelievable. And even when you look at this, if I have 155 points, I calculate 155 buffer distance. I have one covariate for 1 point. And for machine learning, it's no problem. A technique like random forest. Yes, please.
So you take into account know where you are.
Yeah, I can run it here in the code. Let me see. So here's the buffer distances, right? Let me run this code. This takes a bit of time. You see, it takes and it pulls up in a RAM, I think. It will pull up in RAM because I'm not running it in parallel. No, actually, it is running in parallel, looks like. But it takes 5 seconds because I create 155 maps. If I have 1,000 points, I need to create 1,000 maps. And let's plot one map. Let me see. Yeah. So let's plot, I don't know, this one. So this is a buffer distance from a point somewhere, I don't know, here, this point. Yes. So I have 155 buffer distance. I mean, I can go to some other point, I don't know, 28, and it's all different. So you're moving around, right?
Yeah.
And so these are all just buffer distances. Yeah. Yes, here no, nothing. That's random forest. As long as if it's non-linear or skewed, it will try to get to the data. No, nothing. You just throw it, and you get a high accuracy. So and here's now the model. And it estimates that it explains 50% of variation based on out of bag, which is already probably that's the estimate. And then you make a map, and so it looks like this. So here's so it looks like basically like a Kriging. And I can plot. I plot it already in the. I did plot it in the. Let me see. I didn't check with the Leandro the what's up with the, but I will just copy here. So let me copy all this stuff. And we can open it in Google Earth. Let me drop it from the. So here's the prediction. I just plot it now in the Google Earth. And we can see the points and the interpolated values. These are the basically observed values. And this is the interpolated. And so it looks like it's creating interpolation. Even this point, you see, it's a higher point. It tries to come close to that point. So it's a really magical that without any geostatistics, you can go and make predictions. I can play with this. What's very nice in Google Earth, of course, you get this super high resolution. So if I set up a transparency, you could actually, let's say if this was heavy metals, and you can see whether there's a town or something. So you say, oh, wow, we have a really, people have to be careful here, right? So you can see whether it overlaps with town. Also, what's very nice, you see here, predict water. Then you say, oh, what's going on here? Why did we predict water? Well, we can look at the time scale, let's say here. So we can go back to the time, and we can see that actually this used to be, it's very dynamic. So sometimes it floods and the water goes up and down, and sometimes so it's very dynamic, this area. And if I go maybe way back when they did the sampling, maybe then maybe it wasn't water body. So you can also scroll through. You see how the water changes. So that's also good to important to be able to interpret the results and see how do they match with the actual space. And you can play with looking at it 3D or space-time. So so that's this data set. So you said you never experienced anything like that, and yeah, we made a paper, as I said, and this is this paper. Where was it? The paper? Where is it? We made the paper, and then we also made this tutorial, and then I kind of worked out. Okay, that was just a quantitative variable. Now let's look at the categorical variable. Let's look at the extreme values. Let's look at the space-time multivariate problems. And then I saw, wow, this random forest, you can use it as a really generic case. So you can use it generic case for a spatial interpolation. And it's horribly direct, you know, it's and kind of demotivates you to learn geostatistics, which I don't recommend. I think I like the idea of fitting variogram, you know, variography. It's very good because you can you fit something and you understand, and you have a proof in the model that there's some spatial dependence up till what range, etc. So I do still fit variograms, but I don't use it to make the predictions. I don't use it so much. This paper here. Yeah, so that's the paper we published, and it has a lot of attention, and many people now test similar approaches. And the other approach is even more brilliant. A colleague from Belgrade, he made this approach with using distances to the neighbors. So you calculate the distance to the second, so the first, second, third, up to 10th neighbor, and then also the values of the neighbors. So, and that even closer to geostatistics, but because you use the values of the neighbors and the distance to the neighbors. I just use no distances, right? It's a bit primitive, let's say, but he uses also the values, and he also got good results. And it's also super simple, and he applies it to space-time also. Yes?
It's similar to spatial autocorrelation.
Yes, yes, very similar to Kriging, but you fit a random forest model. I'll show you also how this is done, and you can apply it to your data. At the same time, when I got interested in machine learning, this world champion in Go, he lost. Have you watched that documentary? It's excellent, one of the best documentaries I ever saw. It's very tense, you know. There's the Google team and this person. I don't know his name, but he was the world master in Lee Sedol. So, and he said, "I'm going to beat you guys 5-0." Yes, and you know what was the score in the end? It was a 4-1 for Google Computer, the DeepMind. And he was surprised. He couldn't believe it. He couldn't believe he's losing. But he won one game, and he made some moves. They call it the move for God. He had to make some moves that had never been made. That's the only way you can beat computer. So you go really beyond. And he made some moves, and the computer couldn't. Never had that, because computer is. I mean, it's not. There's no intelligence in computer. Yet we don't have any intelligent computer, right? It's just if it has enough data that does that data mining and find stuff, then it can, implement that knowledge. But this guy had to do completely new move, and that's how he won one game. Then after that, they played some much more complex StarCraft. And this one, they said, no way computer can beat. And also they lost. Because this is way more complex. Like the chess, you know, the strategies and rules that you can explain them in a book on 20 pages. When you play something like this, I mean, the strategies, it's like 10,000 pages, yeah, and even more. There's no end, I don't know. And they also won. And then even these people made the software after this game that they won. They published in Nature a paper where they train the machine to play with itself. It learns by teaching itself. It doesn't even need human knowledge anymore. It will generate, it will simulate things, and it teaches itself. So it plays the games that human didn't even play ever. And it learns from that. It's really scary when you think about it. And so the things are really taking off. So we are somewhere here now. We are somewhere here. And so let's say when the things cross, I don't know what's going to happen. But again, in that plot, when you look at it, it's most likely going to be some merger. I don't know. So this is all like really great, right? It's fantastic when you think about this. Very simple. You plug in the data, and off you go. You don't have to think about anisotropy, modeling, parameters, distribution, nothing. But it doesn't work always. So there's also cases when the machine learning doesn't work. And I burned my fingers. You know, I did some maps where I did extrapolation. I created artifacts, and we did some overfitting. And so I learned the hard way about the also drawbacks of machine learning. So number one drawback is the extrapolation problems. Then you have also bias in training data. Data science means data is super important. As you see, the models are secondary. The data is important. So if you have a blunders in data, you have a typo, you know, somebody puts instead of 0, comma, and you get like instead of 5, you get 5,000. And when you think it's a small error, right? But on machine learning, it has huge impact. So you can really just from few blunders, like a 0.1% of data has blunders. They can mess up 80% of predictions. So it's very sensitive to blunders. So you have to spend more time with the point data. So you spend, instead of like in data science, you spend in model-based statistics, you spend a lot of time conceptualizing, picking up the model. Do I use this Bayesian? Do I use this? You know, that's what the analysts spend time. With the machine learning, you have to spend a lot of time cleaning the data. So you do extra actually data mining, and you look, is this an artifact or not? Is it, you know, checking the data? So you have to spend much more time on the beginning and on the after the machine learning. So in a model base, you kind of in the center, you spend the most time, the modeling. But as I showed you here, you don't have to do any modeling, just throw the data, you get the values, but you spend more time on the beginning and the end. So checking the input data, and then after doing interpretation and seeing whether it matches, everything matches the input data and relationships, etc. And so also I did overfitting. Overfitting also a big problem. And then you get the bias. If you overfit, you get the bias. And also then in AI now, they say, yeah, there's a problem in any machine learning you train with the bias data. This bias is going to propagate. And who is going to be to blame? When you run the machine learning and you publish the paper, but the bias is in the training data, you are responsible. Trust me, everybody call me responsible. They never said, oh, it's fine, don't worry, it's the data. No, they say, why did you publish? It was your responsibility to check the bias. Yes, and now also Facebook and all these companies that use this automated face recognition, whatever, for job, they had the model where they will predict whether a candidate will get a job or not. Did you hear about that? And the model just went, yeah, okay, the first thing, most important variable is the sex. If it's a female, cut it down, just take out the males. Yeah, so they go like, you get arrested for discrimination. Right? But the models was fine. I mean, it was because that was the data, but the data comes from the past and you apply that model to the future. And that was a problem. When you do spatial prediction, these are very, memorize this figure. When you have a clustering of the points and you fit a model with the cluster points, and then you slowly start removing for cross-validation, you start moving using only the neighbors which are further and further away to check the models, then they got a plot like this. So if you take the cluster points, you fit a model, you get a 0.96 accuracy, and then you slowly start testing a model. How does it work when I separate the training points from validation points in space? That is called a spatial cross-validation. And they saw this, that it actually drops to 0.5. So it's a really big difference. Imagine here, 97, 52. It's a 50% overshooting. But later on, they saw, okay, this thing, when you move points further and further, it's also eventually you create a too pessimistic estimate of your model. It can be too pessimistic. You force your model to be too strict. But let's say the truth is somewhere in between. So probably their truth is that they have maybe 60% accuracy. If they would just randomly throw the points in an area and estimate accuracy, they will get maybe 60%, but they got 97, So that's why it's also important to apply that. Now, this is a famous example. It's called, it's a little blog that person wrote, Peter Ellis. And it says random for extrapolation stuff for the trees. Have you ever seen this? So what you see here, this is a simulated data set, point data set. And if you fit a linear regression, you can predict out of the space and you will predict the values are here. If you do random forest has no structure basically, assumes no structure. That's why it's very nice, it's very flexible. But the drawback is, because it assumes no structure, when you come to the edges of the training space, if it goes beyond the edges, it can only use the last element. So it says, well, this is the last element, so it must be this. And basically it predicts all the values from the last element. And this thing people don't like, of course, because you see, look, this data has a structure. It's a very clear structure. And the random forest predicts this. So it loses that structure. And we feel like, oh, this is overshooting. It means anybody applying this model to decisions with extrapolation, it's making a mistake. Well, most likely, we don't know in this case, it could be some models, they have this break, But let's say if you have 100 people and you vote, you tell them, vote, which model would you use? 100 people. 100 people will say, I use the model on the left. Okay? So we can do that. We can play with this thing. So this is the extrapolation overfitting. So we can play with that. And I wrote this little post in the Medium. So let's see. So here's this post. You can read about this. I don't make it as R code, but more like in a human language. I explain all the things. But we can also play with this in the R Studio. And so we basically this is the simulation of this model. And so what I do, I say x is equal to y is equal to x plus the noise. Very simple. That's so basically I simulate a perfect linear model with just the noise component. Yes, and then when I go and I fit a linear model, I will get the R square of let's say 0.85. And you see the RMSC 11.8. You see this RMSC should match this one here, so it's almost close to the 15. So it's a proof that a linear model for linear structure, it will do exactly what you expect. So it will estimate the correct RMSC, and it will say that, yeah, 85% of the signal is the noise. I could have increased this noise if I had a higher standard deviation, then the noise component gets bigger and bigger. So that's a very simple way to reconstruct that. And then we fit a random forest. Yeah, so imagine, so now I'm teaching you random forest, great, you can automate it, you can retire earlier, you just throw your data and you come back and, oh, here, projects delivered. But look at this now, we get about the same variance explained, and there is a package called random forest, allows you to also estimate the prediction errors for anywhere in the plot. So we do this random forest, we fit it, and we actually get the RMSC of the random forest is a bit higher, 14. But it's about the same. It corresponds to the 15 simulated. And then when we plot it, here's a nice plot. So you see the uncertainty of the linear model. So not uncertainty, you see the linear model fit the red line. And now what happened? And this is where the problem starts happening. So you see the blue line is the random forest. So first thing about the blue line, it oscillates up and down. Okay, and that means that this random forest is trying to fit the noise in a way, right? Because it goes up and down, like it tries to fit the noise. If I make another simulation and I repeat this, the curve will go somewhere else. So, and it basically randomly goes up and down because I know that's a simulated noise. I know it's a noise. And even bigger problem is if you go to extrapolation space, you have this last element. And then you apply this random forest error formula for uncertainty, and it puts that the uncertainty here, it's lower than uncertainty where I have the points. Where I have the points, the random forest error gets the uncertainty, let's say, relatively correct. But as soon as I move outside, we have a problem. And this is a visual explanation of the two main problems of machine learning that will happen with you if you blindly throw the data and just run random forest without thinking what am I doing here, and do I have some clustering problem, do I have some structure that I'm ignoring, etc. How much am I extrapolating, etc. And so that's a problem, and that's many people say they're really basically criticize, and they really find it, you shouldn't be doing that, And so what is the solution to that? How do we prevent this overfitting? How do we solve ourselves? So many things, you can do many things. Number one thing is to be aware that there's overfitting, and then there's extrapolation, and then to try to see how much you're extrapolating. Where will be the extrapolation? And Hannah Mayer made this little functionality to estimate so-called area of applicability. And this allows you to see which of the pixels were extrapolating. So first you should be aware how much. Is it like 10%? Is it 50%? Sometimes most of the pixels are extrapolating. So you have to consider. Then the other thing is this book by Chris Molnar, fantastic book online. It's also Git book made in R Markdown. You can read all the diagnostics you can do to analyze the models and to see whether there are strange things. And one of the classical things you do is partial dependence plots. Yes, so you can if you fit a model, you zoom in, you do lots of diagnostics. After you pressed random forest, they say, okay, I got the model, I got numbers, blah, blah, all automatic. But now I want to see, what did I get? How does it look like? So you can plot, this is the machine learning fitted regression. Yes, this line, and you see the uncertainty of machine learning. And you see where the extrapolation, it grows. So that looks okay. But for example, here, I have this curve going down and it goes up. Do you see this curve that goes down and then it goes up? And this doesn't make any sense. I know from physics that once I have, for example, bulk density, if it goes lower, bulk density, then the carbon goes up. It cannot go, bulk density cannot go up again if I have more carbon. It never happens. Almost physically impossible because of just how you compress matter. So I know that there is a problem here. This doesn't match any physical law. So I see there's a problem. This curve going up, it's a problem. How do I solve it? I don't know now, but at least I detected there's a problem. And one way, you could say okay, the easiest way, if it's machine learning, you can add more points, you can do more measurements, so I have a higher organic carbon, and then I add more points so that the model goes, okay, and then adjust, right? That would be one way to feed it with more data. But maybe you could also, limit the prediction to the point where the model starts going strange. So you could say, well, I only predict to these values. And I don't predict because I know the model doesn't do well. So these are all these remediation techniques. Universally, both for the extrapolation and for the overfitting, I found out that one mediation technique is just to do ensemble. Just doing ensemble helps me prevent this overfitting. And I want to show you that with this data set, I can show you, because now I switch to the MLR. And MLR is a framework that I'll use in the afternoon for the ensemble machine learning. And so here I can say, well, I'm not going to do only random forest. I will also do GLM. I will do GAM boost, and I will do kernel support vector machine. So I do 4 techniques, which are very different. They're very different techniques. They're really different ways the data is used and how the parameters are fitted. So I will use 4 techniques, and I specify that as a task. In machine learning, that's called a task. And then I specify that I want to do a stack learner. And I will explain you afternoon what is a stack learner. So, and I specify that I want to do stacking by cross-validation with the refitting. And then I feed that model. Now there's a bit more code, and it's also a bit more computational. Even like the small data, it computes maybe 2 seconds. And here I get this model, and this model shows that I have 0.85, and it shows, okay, R square residual standard, it's similar now to the linear model. So, and now I can plot again that, I can plot it. And do prediction. So it's way more code. So definitely more code, more computing. And then I plot it. And let's say this is now comparison between, if you remember the last model and the ensemble model. So here I go, I do now machine learning, but I do ensemble. One of the models I use has a simple structure. It's a linear model. And this model, of course, when I look at the result of machine learning, so here's the summary, this one. If I look at this model, you see that this stacking find out that the random forest actually, it's so badly, it's so least important that we could remove it. If it doesn't have a 1 star, it has to have 1, 2, 3 stars that makes it significant. So support vector machines and random forest, I could remove. Yes, but I don't remove it manually. I got it from the modeling. So I could do extra code to remove all the learners that don't match. Then I rerun it. And then in this case, I didn't remove it because when they have a small, so this beta, you see, beta is very small, 0.7. And the beta for the GLM and for GAM boost is 0.4. 4. So it's about 80 times bigger. Okay, it's about 80 times bigger. So I don't even have to remove it. The beta is so small that it has no impact on prediction, or minor impact. And then when I plot it, we get this one. And now let's do some interpretation. So are you more happy with this plot? Why are you more happy? So the uncertainty, this uncertainty estimate is really wide. It's really wide, right? Maybe it's even too wide, but let's say in this case, because we want to use nonlinear methods, we don't take out the random forest. We want to use it nonlinear. And then we see that between different methods, values go up and down. And then you say, well, the uncertainty is high. The fitting of noise is much, much less. The blue line is almost close to the linear line. It does, however, predict here a bit higher values than linear model and here a bit lower. So it does predict values going this way. If I repeat this many times, every time I will get a bit different curve. You can test it yourself. That's a nice thing to do as an exercise. Change the seed value and just rerun it. Put another number, rerun it, and then you will see the curve changing. You can play with that curve. And this way you learn also. You are basically doing machine learning on yourself. So you learn about how these things change. But definitely sounds like this could be a remedy for the extrapolation and for the overfitting. So it could be an ensemble in itself. It's a good, let's say, remedy. Even better would be if I would add a function here to remove the learners, which have a very small beta. Yes, I could just remove them because otherwise they increase the uncertainty. Yes. So I could remove random forest support vector machines. Actually, I can do it now here. Let's see. So I basically rerun, everything is the same. Everything's the same. I just go in where I define the learners. I can put a new line. Maybe I'll have to restart my session. So this one, I go like this, and I mask out this one. And here I have to now remove, let's say, if I remove Ranger. Things are not what you see, what you get. And let's say I put here on the end. Something like this. Okay, so I changed the list of learners. And if I then rerun the whole thing, let's see. I have to go step by step and rerun. Okay. And net see. So I made a typo. Okay. I rerun this one. And then I get the summary. Let's see the summary now. I still have only 2 learners significant. This nnet, it's less significant. But let's see now the uncertainty. And here's the new plot. So now the uncertainty, see, it's a much more narrow. Do you see? But I don't use any random forest support vector machines. Do you see this? So uncertainty is way more narrow. Okay, so that's the effect of if I would, for this data, if instead of just universal, so it's a universal space-time function, it will work with any GDAL compatible data set time series. Okay, but of course doesn't make sense to use it only for spatial problems. You have to have at least 3-4 times, you know, then you use it. And also, by the way, when you do space-time, how many time repetitions do you need to do space-time? What do you think? How many repetitions? So if I look at some feature and it's changing through space-time, this is the time, right? So I look at some feature, and this is a space. Now I plot it other way around. In space, I put only one dimension, like x or y, the latitude. This is the y, and this is time. So how many points I need to be able to do space-time regression? How many points spread in time? Repetitions, or what do you think? Is it okay if I have 2? If I have like something like this? Can I do space-time regression? So I have like just two years when there's observations or something. Sorry? Well, technically you could, you throw it in machine learning and you will get a model, you know, but think about this. Imagine how time is not time, but you want to model distribution between, so based on the size of the shoe, you want to predict somebody's weight. And there is the longer foot you have, the taller you are, right? So it is, let's say, close to linear. So if you have 2 points, you could fit some linear model. But you could make a lot of mistakes, very tricky to do with 2 points, right? So if you have three, let's say, 3, then linear structure is fine. But as let's say the structures are more complex, then if you don't have enough time repetitions, it's really on the edge of doing space-time. And I just want you to be very careful, because with today with the R and machine learning, you can just throw data, you just throw the data and you get a model, and people say, wow, great, I got the model, without thinking. And many people I see, they hurt themselves with machine learning. When I say hurt, not physically hurt, but they hurt in a sense they make, let's say, overshoot with conclusions, they overshoot with confidence. All these things I show you with the simulated data set, it applies also to complex data sets, or the underestimating the extrapolation error, overfitting the noise, everything applies, and creating artifacts, yeah? And so all this applies, and synthetic data applies to the real data. And so that's why, be careful. If you have 2 repetitions time, probably I wouldn't do space-time, even though you can fit the model. So the question is, can you do it? Yes, you can. But should you be doing it? 80% of cases, I will say no, don't do it. 90%. Either you get extra point in time, or you just say, I cannot do space-time. But maybe in some extreme cases, you could allow, if you know that it's a linear structure, maybe I would allow it. Will the random forest algorithm use of all covariates or select some of the, will the random forest use all covariates or some? Yes, you can do a covariate selection. It's called feature selection. I didn't run it here, but there is a code in MLR. Also, if you have 300 covariates, it will run a learning process to remove the covariates that are not significant. It's similar to stepwise regression and all these methods. It can be also forward looking, or backward looking, or forward backward. And you can run it, and often we reduce 50%. When you have a lot of covariates, you can remove 50%. Often, sometimes you remove only 10%. What measure of uncertainty? This one that I was showing you in this plot, the measure of uncertainty is the prediction error. So that's the error simulated, predicting by doing a random sampling, simulating what will be the actual difference between predicted and modeled. Predicted and observed. This is the measure of uncertainty. There are different measures of uncertainty, but most of, when you do predictive mapping, most of us are interested in the prediction error. And prediction error is at the location. So for any new location, you would like to know for every pixel, what is the prediction error. If there's no more questions, we can stop with the YouTube. I will stop with the live YouTube. Let me see. I have lots of in the chat also. Okay, people complain about the video, problems with installing the VirtualBox. Okay, I will come back to your questions, but for now I have to stop. With the